In this video, we're going to take a look at a new term for us. It's called the circumcenter of a triangle. And it's kind of a cool idea, so let's go ahead and take a look. So we're going to investigate this idea of the circumcenter of a triangle by using GeoGebra. And what you can see on the screen here is I got a triangle. And this triangle, there's nothing necessarily special about it. It's just a triangle. And I'm going to go ahead and plop on there I'm going to put the perpendicular bisector of, let me see if I can grab it, the perpendicular bisector of one of the sides. So I'm going to use side A here, and I'm going to put the perpendicular bisector of side A on. Now remember, perpendicular bisectors, they bisect segments and they're perpendicular to them. And you can kind of visualize that's what's happening here. My perpendicular bisector, it looks like it's cutting segment BC into two equal parts. There's a right angle right there. Okay, so that makes sense. That looks like a perpendicular bisector to me. Now if I move the corners of the triangle, you can see that perpendicular bisector is going to kind of maybe change the way it looks because it's always going to be perpendicular to segment BC there. So if I change where C or B is, it's going to move that perpendicular bisector. So let's put it about like that. Now I'm going to go ahead and do the perpendicular bisector of one of the other sides because I could do the perpendicular bisector of each side of this triangle if I wanted to. So let's do another one. Let's do the perpendicular bisector of segment AB. And we're going to go ahead and put that on there. And you'll notice now that the two perpendicular bisectors are intersecting. And let's go ahead and put a point at that intersection. So I want to grab my point tool. And I'm going to put the point of intersection on there as point D. Now it makes sense that those two objects would intersect. They're two lines. The lines are not parallel. So anytime two lines that are not parallel that are in one single plane, and anytime they're not parallel, that means they're going to intersect, right? So we expect those two perpendicular bisectors to intersect. If we took a look and we moved around the corners of this triangle, you can see that because I'm changing the shape of the triangles, changing kind of the way the sides are angled, that those perpendicular bisectors are moving around. It looks like sometimes that perpendicular bisect, that intersection of those two, is going to be inside the triangle. Then if I make it maybe a more obtuse triangle, then that intersection moves outside the triangle. Sometimes I could probably make it to where that intersection is right on the edge on one of the sides of the triangle if I really wanted to. But let's keep it as an acute triangle so we see that intersection inside the triangle. So now here's where the really cool thing happens. I've got two of my perpendicular bisectors on the triangle. Like I said, I'm not surprised that they're going to intersect, right? We would expect them to intersect because they're going to be two lines that are not parallel to each other, so they're going to be intersecting. But now let's put the third perpendicular bisector on our triangle. And so I'm going to put that third perpendicular bisector, I'm going to put it on segment AC, so I'm going to tell my program to create the perpendicular bisector of segment AC. And what you should notice there is something kind of interesting happened, right? What we have is we now have point D, which is actually where all three of those perpendicular bisectors are intersecting. We expect two of them to intersect when we put two on there, but it is kind of interesting that when we put all three perpendicular bisectors on, one for each side of the triangle, that they all intersect at one single point. So our next question is, well, does that happen just for this magic triangle that I have on the screen now, or would that happen for other triangles? So let's go ahead and start moving around the corners, and you can see that if I move around the corners of this triangle, it still is going to happen so that the intersection of all three perpendicular bisectors is at one location. Again, if I make it an obtuse triangle, that location of that intersection is going to be outside the triangle. If I really work hard at it, I can probably make that intersection to be right on one side of the triangle. If it's an acute triangle, that intersection is going to be inside the triangle. So this will take us to this Theorem 5-5 that you can see off to the side of my screen Let's go ahead and complete that statement. It starts as saying the perpendicular bisectors of a triangle. Okay, we know there's going to be 3 perpendicular bisectors of a triangle, 1 for each side. What we're going to be able to say is that they will all intersect at a single point. The perpendicular bisectors of a triangle will all intersect, and we call this, they will be concurrent. That's the kind of more technical term for that. They will all intersect at one point, and that point is going to be called the circumcenter of the triangle. The circumcenter of the triangle. And that is part of the idea for Theorem 5-5. So we can see that those 3 perpendicular bisectors are intersecting at one single point, but we should be able to take it even farther than that, because, let's think, this point D, let's think about point D, and let's think about segment BC. Okay, so point D is on the perpendicular bisector of segment BC. That's this line here, line F in my picture. It's on the perpendicular bisector of segment BC. So according to what we learned in one of the previous videos, that point D should be equidistant from the endpoints of B and C. And let's in fact go ahead and show real quick that it is. Let's go ahead and measure the distance from B to D and from C to D. And we can say in this case, the way I have my picture arranged right now, it's 4.03 units from each of those endpoints. D is 4.03 units from B and 4.03 units from C. And we would expect that to happen because we learned that any point that's on the perpendicular bisector of a segment should be equidistant from the 2 endpoints of the segment. But now let's take this a step further. D is not only on the perpendicular bisector of segment BC, it's also on the perpendicular bisector of segment AB. So what we would expect is that D would be equidistant from both B and A. Well, we already know that from B to D is 4.03, so what we would expect to see is that from A to D is also 4.03. Okay, so interesting. What does that tell us? It tells us that this point, the circumcenter of our triangle, it's the same distance away from B as it is from C as it is from A. Another way to say that is that the circumcenter will be equidistant from all 3 vertices of the triangle. And so that's the kind of the second important part that we're going to add to this theorem. This point, meaning the circumcenter, will be equidistant from the vertices of the triangle. So here's what we got, just to kind of wrap that up. When we draw the perpendicular bisectors of a triangle, of course, that means we could draw one for each side, so there would be 3 of them. When we draw those 3 perpendicular bisectors of our triangle, they're going to intersect at one single point. It's called being concurrent. That one single point there is called the circumcenter of the triangle. And what's special about that circumcenter is that it is equidistant from each vertex of the triangle. Now there's one last thing I need to tell you about that's special about that circumcenter. That circumcenter is also going to be considered the center of what we call a circumscribed circle for this triangle. Let me write that term down here real quick. It's called a circumscribed circle. Circumscribed circle. A circumscribed circle is a circle that contains all vertices of a shape, or of a polygon, I'll say. So a triangle is one example of a polygon. It's a 3-sided polygon. So that center D is going to be the center of a circle that would have A on it, it would have B on it, and it would have C. Let me just show you real quick what that's going to look like So I'm going to go back to my GeoGebra and I'm going to select the Circle tool, and I'm going to choose to make a circle that has a center at D that goes through C. And what we're going to notice is I told my program to make a circle with a center at D that goes through C, but it also goes through A and through B. And the reason why it would make sense that it's going to do that is because the radius of a circle, right, the radius of a circle is the distance from the center of that circle out to any point that's on the circle. So the radius of this circle that I just created is 4.03 because I told it to have a center at D and have C on the circle. So that distance from D to C, 4.03, that's the radius of the circle. Every point that's on that circle is 4.03 units away. And in fact, every point in this plane that's 4.03 units away from D is on that circle. It's not possible to find another point in the plane that we're looking at that's this far away from D that would not be on this circle. So all the points that are 4.03 units away from D are on the circle, so that would mean it has to include A and it has to include B. Therefore, that circle has to be the circumscribed circle for this shape. And again, just to kind of show you, if I were to change the shape of my triangle, start moving these corners around, you'll notice that every time the distance from point D out to the vertices, it's always staying the same, even if I make it this obtuse triangle here with an angle of more than 90. Point D gets outside the triangle, but it's still the same distance away from all the corners, and that circumscribed circle still exists, where it has a center at D and it contains all the corners of the triangle.